Hello, good afternoon, everybody. I will be starting the lecture now. There are still a lot of students missing, but I hope they will join in a few minutes. Since it's already 5 minutes past the start, I don't want to have you make you wait for them. For today, the main topic that I will be discussing is the memory management. I think I have started it last week. Can you confirm that this is the case and also remind me maybe on what I have managed to discuss before the end of last class. So I will share the screen. All right. So you should be seeing now my slides. If not, please someone let me know that something is wrong, but I hope not. So you are seeing this first slide, and I hope that you remember about building the core image, about the different stages, the compilation, linking, and loading, because I distinctly remember that I have covered those topics. And I think that I have ended not finishing the slide I am showing you now. If I am wrong, then please let me know. Okay. I don't hear any disagreements. I hope that is the case. So let's start back to remind you what I have been talking about. I was discussing how the memory is created when a new program is being built. And of course, the content of the memory, how it's organized, that is something which is managed by the compiler. The compiler reads your source code and converts it into instructions in the machine code. That's the definition of compiling languages. In case of most common architecture nowadays, that will be that it is converting the code into 8086 and later Intel processors. So this code, that's just after conversion, it's still just bytes of code, nothing else. Okay, so the source program, when you write the source program, when you compile it, the compiler builds object modules. That means modules which are partially compiled already, so partially it is converted. All the high-level language instructions are changed to low level. All the constants that you use in your program are also converted to some bytes, and also all references to functions, references to variables, they are converted to addresses in the memory. But of course, when you compile a single module, you don't know yet what will be the full program, because program always consists of a number of modules. Even if you build a single file program, which means that you have only one compiled by you module, then afterwards when you are linking it, other modules will be added, modules from the library. Okay, so you have some modules which are built directly from compilation by you, and you have additional modules which are added by extracting from static libraries. each module no longer contains the high-level language code that you have written. Instead, everything is translated to machine code, but okay, all the addresses are converted also, but not all of them. Okay, some of the addresses cannot be converted at this moment during compilation because you don't know where in the program the function or variable that you are referring will be situated. Okay, that depends on where it was declared, probably. If it is in the same module, then you do know, but if it is in a different module, then you need to determine that later. Okay, so that is more or less how it works. And the important thing is that for the conversion purposes, there is a very nice distinctions between the variables. Okay, if you have local variables, which can be used only locally in a single function or in a single module, then those names disappear during compilation. But if you have variables or functions which are in other modules, then at the moment of compilation, you just know that they are elsewhere. You don't know where, so you cannot convert them. And because of that, such references to variables or functions outside the module, they are called external addresses. Okay, because whether we are discussing functions or variables at this point is not important. It's important that they are addresses in your code somewhere. Okay, so in case of external variables, when the compiler builds the object module, it builds something which is called external references table. In that external references, you have information where from within the compiled program a reference to that variable has occurred, and for each such situation, and what is the name of the variable or function that you need to refer to. Okay, so that is the external symbols or external references table. Okay, another table is built also during compilation. That's the compilation of global symbols. Global symbols are those variables, those functions which can be referred to from outside the module. In case of C, it's simple. For the function, it's all the functions. For variables, it's all the variables which are static, declared as static, and they are declared outside any other function. If you declare a static variable inside a function, then it's not global and it cannot be referred from outside. But if you define it outside the scope of any function, then by default they are global. Okay, so any global symbol can be used from other modules. Of course, to use them, you need to define them in the header file, but that's something that you know, and it's something that I don't want to discuss unless there are questions about it. Okay, but the whole point is that when you compile the program, the compiler will find out in your source code which symbols, that means variables or functions or classes or structures, any objects as well, which of them can be referred from outside, and all those symbols will be packed inside a second table, which is called the global symbols table. Okay, so inside each module, we have two tables. One table of external references and one table of global symbols. Okay. If there is a reference from one, if there is a common position in both of them, it will immediately disappear from the external references, because it wouldn't be an external reference, but a reference to a global variable in the same module. So such references will not appear in our external references. Okay, so that way you have modules which then you have to combine. Combining the modules means that memory needed for the code, memory needed for variables, and so on, they are grouped and they are combined together. That's the first thing that is being done. But the second, more interesting thing is that the global and external references are compared. So for each external reference, we look in all the global symbols if it is defined. If you find a position where it is defined, then in the global table you have the address. In the external, you have the location in the code where the references was being done from, and you just remove the position from the external references, instead writing that address inside the address of the global symbol inside that reference point. Okay, and that way you already have a compiled program which knows where to jump to. Okay, this is done, as I have said, during the linking, and it's the most important part of the linking. Okay, once you do all this this matching, you will find out that there are still some external references in your source code. So even though you have already combined all your source program modules, you still see that there are some references missing. And then the linker starts looking through the static libraries. That means the libraries which contain pre-compiled modules supplied by the producer of the library. So you first of all access the first module, look inside it, you get a global symbols table and external references table. You look at the global symbols. Is in this module any symbol that you are missing in your partially linked code? If there is such a global variable, then you combine this library module, meaning extract it from the library, because a library is just a collection of modules compressed and so on, so it needs to be extracted by decompressing. But once you do that, it is just added to your program and becomes part of your program, even though you haven't written the code. Okay, so the the library modules are being combined with your binary code at this level. Of course, when you add a new module, there may be some external references in that module, so you add them to the global external references table, and there will be some global symbols, and you add them to the global symbols. All external references to the global symbols are then satisfied and removed from external references table. At certain point, okay, so you have analyzed the first module, then you go on to the second module, check the same thing. If there are no external references in your program to the to global symbols in this, you just ignore it and go on to the next module and so on. At certain point, your external references table will appear empty. If that is achieved, that means that you have successfully linked the program and you no longer analyze the static libraries. So you see, during this linking process, parts of the libraries that you declare for linking in the command line, parts of those libraries are copied to your executable file, and they become part of the executable file that you are using afterwards to load to run the program. When you start running the program, you invoke something which is called a program loader. That's again a library function, usually invoked from the shell or from the graphical user interface, and this function takes the executable file and loads it into memory. Actually, at this point, the addresses in your executable are replaced by addresses in the physical memory. That means during loading, your program, the executable is analyzed. Any points that need absolute references to addresses are fixed at this level. If you have relative jumps or relative addresses, they will be satisfied automatically. You don't need to worry about them. But if you have absolute addresses, then they become absolute only when you know where in physical memory your executable is loaded to. At that time, your executable actually is changed, copied, but not one-to-one, but you change the address references from the addresses which are calculated on the basis of the beginning of each segment in your program to addresses which are absolute in physical memory. And when that happens, when you load the program into memory, it is something which is called core image. And actually, I don't know why there are two different references, but it's exactly the same thing as we were speaking about when we were talking about process context, because the user context of the process is exactly the same as the core image. But of course, during execution, the user context is changing, whereas the core image is the image that is being produced during loading. So It's the initial state of the user context of a process, which will then change. Okay, so that's more or less what happens. And as I have said, a very important part of this is that you always have inside the operating systems some libraries that you will be using. Static libraries are analyzed during linking of a program, and a program which is already linked to the executable doesn't know what static library, each function, each code was extracted from, because that's not important. What it does know is that there is a copy of the necessary modules inside your executable. That means that if multiple executable programs are being executed at the same time and they use the same library functions, then each one is using a separate in-memory copy of the library function. You can determine that some of the functions are already in memory because a different program is using them. So that means that if you have a heavily used operating system where there are multiple executables being executed at the same time, you waste a lot of memory for in case of static libraries, because you have in memory multiple copies. What is also quite important is that the code, the library code that is being used by your program is also stored inside the executable file, which makes the executable files much larger than they need to be. So that's the disadvantages of using static libraries, but there is also a very clear advantage of using static libraries, that is that your program is not based on any other files except for the executable when you run the program. Okay, but static libraries is just one of the approaches which that can be used. There is another approach to and another type of libraries, the so-called dynamic libraries. That's a name which was introduced by Microsoft, really. The DLL file is such a dynamic library. So DLL stands for Dynamic Link Library, and this is something different from the static libraries. Okay, in case of Linux system, okay, they use a different name for those libraries. Since I will be telling you in a moment about its advantages of these libraries, so they have based the name of one of the most important advantages of using such libraries. That means that you can share the same code in memory. Okay, so you avoid the multiple copies that occur in case of static libraries. So this type of libraries, in case of Linux, they are called shareable objects. It's the same, exactly the same idea. The only difference is with the formats, of course, because each operating system has its own formats, how to store such libraries. So they cannot be interchanged, but they work exactly the same. Okay, so what is such a library? It's a separate file. Okay, it's not linked statically, as I have said before. Instead of that, when you are using a dynamic link library, you just, in the executable, you just remember the name of the library that the function should be using. Okay, so during normal compilation and linking, there will be some references which are not satisfied. Instead, the linker will enter inside the exec file. It will enter information that this address, it's an address inside, for example, the inside the stdin DLL or whatever, or window DLL. There's such a DLL because I don't think there is a stdin, but there is a window.dll. So there will be still an address, but this address, in case after linking, will be the address consisting of two parts: the name of the library that you need, the dynamic library that you need, and the offset from the beginning to that library. If something like that occurs and you are loading your program, then the loader will check whether there is a copy of the dynamic library in memory. Okay, if there is one, it will not do anything except that all the jumps to the dynamic library will be translated to references inside that library. If a dynamic library is not in memory, the whole dynamic library named will be loaded into memory, and then it's already in memory, and the same situation will be doing. So the important thing is that the code of functions, of variables, of data blocks, which are contained inside a dynamic library, are not copied into the executable. Instead, inside the executable, you have just information that a dynamic library is required and what is the address inside that library that the reference refers to. So this library, as I have said, must be loaded at the same time as the executable. But if the library is already loaded by some other running program, the new program being loaded will reuse that library which was earlier loaded. That means that there is just one copy of the library in memory, and this is a very distinct advantage of dynamic libraries. There is another advantage of those types of libraries, that the code is never inside the executable. There is, I am afraid, also a disadvantage. The disadvantage is that often the dynamic libraries are distributed separable from the executables, because if the executable is using a standard library, so the producer of the executable will not be supplying you the library. Instead, the operating system or some other package will have to be installed with the dynamic library. And that means that the upgrades of software are not connected with upgrades of the libraries. And that means that even when you are not doing any upgrade of your software, but you have done some upgrade in the operating system, some menus, some windows might suddenly look different. That's because the dynamic libraries will contain somewhat different code from what they were using earlier. So this is a problem, and sometimes to maintain programs which were not very well written, but which require specific versions of the dynamic libraries, you end up with keeping in your system different versions of the DLLs and having problems with collisions because different programs are using different ones. Okay, so that is a problem. There is also one thing more that I need to tell you about. That's the stub libraries. Okay, in Windows, that's a separate file. So for each dynamic link library, DLL, there is a stub library in the development tools when you want to use the library, and the way that you use the dynamic library is actually that you link statically to the stub libraries. The stub libraries contain information where in the dynamic link libraries each global symbol from the DLL is actually located. Okay, so those stub libraries are used during linking of the exec, and from that stub libraries, the exec gets information about the offsets where it needs to jump to the DLL. In case of Linux, actually, the shared objects library combines a dynamic library and a stub library, so you don't get two separate files, or you can actually, because you can do a lot of things by manipulating commands, but by default, when you get a SO library, it is at the same time the development library onto which you statically link the stub libraries, the stubs, and also during runtime you use it the same as the LL. That means you load it into memory. Okay, any questions to this? Okay, so the next thing that I wanted to talk about is something which is called executable loading. I have already mentioned that when you want to run a program, you need to first of all open a file, the executable file, then the loading program, the loader, the function which loads the program, determines how much memory your program requires. This is something that compiler and linker provide in the header information inside the executable. So this memory is being allocated by the loader function, and then information is copied from the file into memory with global references being resolved at this time. Okay, this actually can take quite a long time. Well, that means it might take a few minutes, so not so very long time. But the problem with static loading, as I have mentioned, as I have described, is that usually a lot of programs are being loaded when you start the system. If you start the system, whether it's Linux or Windows, the first thing that happens is that the initializing system initialization starts, and inside there you have scripts, you have, in case of Windows, you have lists in the registry also of what commands has to be run. Okay, and all those programs connected with those commands are being loaded into memory, which means that static loading during startup of the system can take quite a long time. Okay, single program takes a few minutes, but if you are starting 20 programs, you suddenly may get into a situation that your system is starting for half an hour before you can work on it. This became a big problem somewhere with Windows XP, so a little before that. So at that time, Microsoft has introduced another concept which was previously known, but not used by Microsoft, which is called dynamic loading. Actually, the idea of dynamic loading is quite simple. Okay, if you want to run a program, you don't really need to copy everything from the executable file to memory and then jump to an address inside the memory and start executing from there. That's how static loading works. Okay, so in case of dynamic load, you use some trick. You copy just a small part of the executable into memory, and if what you have copied contains the start of the running program, you can jump to that position and start running the program. So at the same time, in this case, you are starting executing the program and still continuing to load it. Okay, because obviously, if the whole program was not loaded before starting running, it will come to certain positions where it doesn't have anything to run anymore because code is not loaded. So when that happens, there is an error. That error is handled by the operating system, and additional fragments are then copied into memory when they are referenced. Okay, so what is the advantage of such an approach? Of course, there is a clear disadvantage. It's much more complicated than static loading. But what is the gain from that is, first of all, sorry. So the first thing, which is the most important, is that the program starts running and doing what it is supposed to do much quicker. The user is not really, it doesn't matter to the user that the program hasn't yet finished loading if it is already running, communicating with him, and doing some task that he needs to do. But what is even more important is that lots of the code in a program might never be used. Okay, that's because nowadays the programs are quite complicated. They offer a lot of features, and the users often don't use most of them. They just use a few functions that they know about, and They just don't bother to learn anything more. And that means that if you copy fragments only of code only when you need them, then obviously there will be parts of the executable file which will not be referenced at all, and that means that they will never be copied into memory. So the two advantages are first, that you use a lot fewer copies from disk to the memory, and that the program starts running much quicker. Of course, there are problems with this. The executable file in this case needs to be available during all the time of the program running, whereas in static loading, once you load the program, you can even delete it and it will still be running in memory. Of course, if you finish it, then the next time you try to load it, there will be nothing to load, but in the meantime, you don't need it. Okay, in case of dynamic loading, the executable file will be needed all the time, because you never know if everything has already been copied into memory or not. Okay, so I have mentioned a few times that there is a library function for loading, for doing all of that. And this library function or loader function is called exec. I have written here two question marks because there is no function in C, at least, which is called just exec. There will be a function called exec_ve, there will be a function exec_p, and so on. So there will be quite a few exec loader functions. They differ, by the way, by the arguments that you provide to the loader function. Okay, so exec_ve is the most complicated. It needs three arguments, that is the executable program file. That means that the path to a file that contains the executable, but it also needs arguments which you need to pass to the program when it is running, and also environmental variables that you also need to pass to the program. In other cases, the executable files are less complicated. The first argument might be either the direct path to a program, or might be the name of the program, in which case there is a special environment variable which is called path, and you you search for the program name in all the directories defined by the path variable. Okay, in some arguments there will be, in some versions of exec, there will be no environment table. That's because the then the table of variables will be taken from the parent program process, which is executing the exec function, and copied. There is a important thing is that whatever exec function you use, you don't use the variables, the tables of variables from other processes. You make a copy of that table. That's something that you have possibly experienced when you were running scripts, that inside the script you can define variables, but you end the program, those variables disappear. That's why? Because you have made them in the local table, the one provided by exec. And When the program ends, the parent program, the shell, will not know about it. Okay, so you changed just in the copy. Okay, one more thing that I wanted to tell you about is something which is program overlays. Once upon a time, quite a long time ago, really, it was a very popular technique. Nowadays, it is still used, but it's not so very popular because the approach used by virtual memory, which I will be discussing, well, maybe not today, but certainly within this set of slides I am discussing it, have made it more or less obsolete. So what is the idea with the overlays? Okay, you can compile a program and you still can compile it, both using JCC or using J++ or using Microsoft Visual Studio. If you are running Windows, all of them have an option to compile a program with overlays. The whole idea of program with overlays is that you take your code inside the executable, you define what is inside each overlay. In C, you use the directives for defining the overlays and which code is supposed to go to each overlay. And then when you build the executable, you make some of the area of your program just a holding area, which is called overlay area. Okay, inside the executable, you have different overlays. Each of them can be loaded into the overlay area, but of course only one at a time. So when you run a program and you jump or refer to this overlay area, the executable, or because as part of your executable, there will be a standard functions for managing overlays. It will not only jump, but before jumping, it will check what is inside the overlay area. If you are jumping to overlay 1, but inside the overlay area is overlays 2, then it will first copy from the executable overlay 1, put it into the overlay and jump or refer to that address. Okay. So this content of the overlay area is changing depending on which overlay you are using. So what is the purpose of that? Of course, memory is always an expensive resource. You know that from phones, you know from PCs, from laptops, that depending on the amount of memory that you have, you will pay quite a lot, higher prices for devices with more memory. Okay, so on the other hand, each program requires a certain amount of memory. When you compile it, it may turn out that for the clients that you want to send the program to, it requires too much memory. It will not be then very popular because nobody will buy a very expensive laptop just to run a single program. So instead of that, what you can do, you can compile your software using overlays. And in that way, the required memory is this And overlay area will be the area of the maximum size of the different overlays that you have. Whereas if you did not use the overlays, the overlays would have the code inside them would have to be all the time inside memory. So it would be the sum of the sizes of all the overlays. And obviously, a program which uses just the overlay area of the maximum overlay size will be much smaller than the program which has all the overlays resident in memory all the time. Okay, so that's overlays. And the problem with overlays is that it requires the programmer to define. Programmer must define the overlays. Programmer must compile and link the executable to provide overlays. If you have an executable, you have no choice. You must use how it was compiled. You just can't change that. If you have the source code, of course, you can introduce overlays and recompile the software to use less memory. But if you don't have the source code, then executable makes you use as much as memory as it was linked to use, and you have no influence to that. Okay, so that's program overlays, which, as I have said, was very popular when memories were smaller. Nowadays, it's much less popular, but also a lot of, especially phone software, is still using overlays. Okay, the next thing that I wanted to talk about is memory allocation. Memory allocation is something that I have said just a few slides ago, that static loading means that you need to allocate memory for the program. Okay, and that is what I'm addressing now: how to allocate memory, how the operating system allocates memory to the programs. Okay, I will tell you about 3 techniques for allocating memory. 2 of them are quite commonly used, but I am starting off with one which is not used for quite obvious reasons, but since it is the simplest approach, I would like to start off with it and only address the others as solutions to problems to this first approach. Okay, so when you have memory and you are loading program, you are loading the program to physical addresses, and inside the program you are using code which jumps to logical addresses. So when you allocate some memory, find that some memory is free, so you say, okay, this program runs in that memory. So what you will do is you need to set up 2 registers, one which will contain the size of this block of memory that you are allocating to the program, and the other which will contain the beginning. And when your program is running using logical addresses, each address, when it comes, for example, when the processor fetches the next instruction to be run, first of all, it will be checked whether the logical address is less than the size of memory allocated. If it's not, that means that you are trying to jump outside the memory that you were allocated. That will cause an error with a memory violation error. This is it used to be quite a common error occurring in software running on Windows programs, that you were getting blue screen, it was called, that memory that memory was violated, and that was what was happening quite often. Nowadays it's less often, but it still can happen. Okay, so if the logical address fits in to the memory that you are allocated, then the processor uses the datum register and adds the logical address, and this new address uses to access physical memory. That means the computer bus to load from memory into to access that memory. Okay. So the whole problem with this approach is, okay, it's quite simple. It is quite fast, because when you have the processor has two registers, which you just initialize when you load the program into memory, and so each time it is being activated, those registers will be set to the values for the process that is running. When you sleep or have active, that's not important. Another process will use those registers. So just two registers are required to two registers on each processor used in the in the system that the operating system is managing. Okay, so this is a very distinct advantage of the approach, because accessing registers is fast. That means there is very little overhead in translating logical addresses to physical addresses. Okay, but what is the problem? There are two problems actually. One problem is that the whole of the core image must fit into a single continuous block of memory. So if there are many programs, it is not easy to manipulate that, and I will show you what I mean in a moment. I don't have this slide, sorry. Okay, I don't have the slide. I don't know why. I thought that I did have it. Anyway, the whole problem is that in this case, you have problems with something which is called fragmentation of memory. If a program is loaded into memory, afterwards a different program is loaded into memory after it, and so on. If one program is released, okay, then the block becomes free, but blocks after it and before it are still used by other programs. Okay, so they are not free. So if you want to use that free space for a new program, you will end up with a problem that a number of programs will not fit into that block of memory. Okay, and you cannot just simply move the programs inside memory, which means that you might end up that you have enough memory to run another program, but the empty spaces are so fragmented that you cannot put them into any one of them. And that is called fragmentation, or actually memory fragmentation. And this is so-called external memory fragmentation. Why external, that I will discuss later. Okay, so this is one problem, but there is also another problem with this type of memory allocation. And this other problem simply means that if your program needs to change the amount of memory it uses dynamically, then you have a problem, because before it and after it in memory are different programs, and you just can't increase the memory. Okay, you can decrease the amount of memory, but you cannot increase it. So dynamic memory allocation becomes practically impossible, or rather very expensive in process of times, because it would require moving of programs inside memory to make more space for the one which needs to resize its memory. So there is a different scheme which reduces the problem, which actually limits the problem of external fragmentation I was telling you about, which is called segmentation. In case of segmentation, the program is not loaded as a single block inside memory. Okay. Instead, if each segment of the program, I was telling you during compiling, linking, that the program defines some segments, fragments of it separately. So during loading the program, instead of looking for a single block where everything can be fitted into, instead of that, you look separately for memory for each of the segments. So the logical addresses in this case are the segment start of the segment, or rather index which identified the segment, and offset inside the segment. For each segment, there are two values, the datum and limit, which I have already mentioned in these cases, but in case of segmentation, these are not registered because there are more of them, and it would be too costly to have register banks to maintain it. So this is in-memory table, which can be only speeded up using some techniques, but it's actually inside memory that the program contains the datum and limit of each segment. So each address, when it is being translated, the offset is checked against the limit of the segment that it's referring to, and then generates memory violation if the address is if the offset is too big, and then it adds the beginning of the segment, the address that is the beginning of the segment, and that's used as the physical address going to the bus of the computer to access memory. Okay, this approach reduces external fragmentation. It does not eliminate it, but it significantly reduces the problem. The idea is really quite simple. the smaller blocks, which must be continuous, the easier it is to fit them into the holes inside the memory, and then you get smaller external fragmentation. But of course, there will always be some misfit, which means that there will be external fragmentation in this case. There is no problem with resizing the program. So dynamic memory allocation in this case is not a problem, because when you run out of dynamic memory in one of the segments that is already allocated, you can allocate another segment, just adding a position in the segments table, and you have the memory. It doesn't need, the added memory doesn't need to be continuous with the rest of the program. Okay. Another approach is something which is called paging. In case of paging, the logical address is split into two parts, the page and the offset from the page. Okay, there is again a table inside memory, which is called the page table. It does not have two parts as in case of segmentation, segments table. It just has one part that is the beginning of each page. So the whole of the physical memory is divided into frames. Okay, so the physical memory is cut into frames. Inside the page table, we have the number of the page corresponding to each logical page address. So the logical address is the page number and offset, and this page number using the page table is translated into a frame number, and the offset is exactly the same. So in case of binary numbers, and that's what we are using in computers, it just means that translation from logical to physical address just means replacing the page number with the corresponding frame number. So at the beginning of the program, the loader looks inside memory for all the frames which are not in use, and is allocating for each page of our program a different frame. They do not need to be one after the other. There is no requirement of any type for that. So that means that external fragmentation is never observed in case of paging. And there is also no problem of dynamic allocation of memory to a program, because if extra memory is required, you just allocate a new page and a new frame to store that that page, and that's all. Okay. There is a different problem in case of paging. This different problem means is that the memory is split into frames, and the address space of the program is split into same size pages. That means if you look in your program, there will be always the last page of your program, which will not be used in full. There will be some part of the page that is unused. Since you allocate memory by pages, that simply means that one of the pages will be the last page of your allocated to your program will not be fully used. So there will be still a hole in the memory that you cannot use for other programs. This will be a part of the last frame in each program. If you have a lot of programs running in parallel, then you have a problem that this small losses from each page will accumulate possibly to quite a large number. Okay, so we have the page tables. There is something else which is a big problem, which is both a problem in segmentation and in paging, and this is how to handle the pages in memory. Okay, the segmentation tables are usually quite small, which means that the problem is not really very big. But in case of page tables, the page tables are often very large. That means that you are never able to store the page table inside registers. Instead, you need to store it in memory, and inside your processor, you just use a small cache that you have of very fast register type memory to speed up. But most of the page table is inside memory. Okay. So if you use such an approach, and nowadays at least Intel processors use them quite exclusively, there are two problems. How much of this cache memory dedicated to this, because there are different cache memories inside the processor, but how much of it you have available, and also how to determine if a page is inside memory or if it should be copied from, if the page is inside the cache or if it should be copied from the memory to the cache to have quick access. Okay. So this first part, the translation look aside the buffer, that's a hardware solution which remembers where what pages are cached. So the first thing we do is we need to check whether the cache is inside memory. Okay, if it is inside memory, then the access time will be just memory access plus the time needed for TLB response. But if you have the page outside TLB, then you need to copy it from memory to cache and then do it. So it's very important how good is the translation look aside the buffer, and that depends really on the amount of memory in cache. So from this you see, if you have a good enough hit rate, then you can lose only a very small amount of time. But if you have a small hit rate, that means that you have too small cache that you are using, then you can even double the time of accessing page blocks, because you first have to read the page table, and then you need to, from the page table, you have to read the in-memory page. Okay. So I don't think I want to start the next part of the slides now, because that will take. I will not be able to finish it till the end of this lecture. So we have about 5 to 10 minutes. If you have any questions, I would happily discuss with you whatever you don't understand from what I was telling you, and we'll start virtual memory discussion next week. Are there any questions?
Yes, I have a question about memory fragmentation. So is there some like kernel mechanism that can sort this thing out? Like if the system runs for the year?
Actually, no. The whole point is that, okay, there is a mechanism, paging. Paging eliminates external page fragmentation, but in its place introduces something which is called internal fragmentation. That means that the last page of allocated memory in each program is not used fully. Okay, but there is no external fragmentation. But that is at the cost of large page tables, which I have said. And if you want to have smaller page tables, then you need larger pages to describe the same memory. And that means that internal fragmentation will become higher, because always internal fragmentation you can expect to be on average half the last page. That means half the page size, so it's proportional to the page size. In case of external fragmentation, that occurs, of course, only in segments allocation and in continuous allocation. Continuous, as I have said, is so bad that nobody now uses it. But the segments allocation is used almost as well. If you don't need virtual memory, it is used just as often as paging. And that's because if you have segments of proper sizes, then the segments table is much smaller. So you don't have those problems with caching that I was talking about. And instead you have, it fits much better into the memory. It runs much better than paging. But as I have said, then you lose memory because there always will occur gaps between the programs. Once you start deleting, running different programs and so on, there will always be gaps forming. If you want to eliminate external fragmentation, okay, that's also important. In case of memory, that's not a problem. You just restart the system, or you just simply kill all the processes, and then the memory will be freed, and you start on again allocating it. So nobody bothers to have any mechanisms for sorting this out, because in-memory programs are only when they are run. So that means it's not a problem that you need to sort out. Of course, we will be talking about fragmentation also when I get to the next topic that will be discussed, that is to the file systems. In that cases, there need to be special mechanisms for removing external fragmentation, but that's a different problem, because the fragmentation is permanent, not only when in case of memory, just switching off the computer removes the problem. Okay, of course it will start off again next time you run programs, but otherwise.
Well, I would argue that things like servers can't have like power strip with the timer that resets them every time.
Actually, yes, they do that.
Okay.
But the whole point is that the situation just means that you are not using all the memory that you have, and nobody is really worrying about it. And that's because it's not permanent. It's permanent in case of disk. So there are mechanisms especially for using it, but not in memory.
Okay, thank you.
Okay. Any other questions?
Excuse me?
Yes.
I had a question about these slides. Are they going to be available anywhere for us to download?
I thought that you have access to them. I will check it today. Certainly, they are. They should be available in the in your this e-learning system of our university.
Okay, they are not there right now, so
they are not.
No.
I will check. I will check that. I thought that I have uploaded, not the virtual memory, not the memory one, because that's running now. But I thought that the previous ones I have uploaded. I will check that.
Okay,
And
we
I
only
will
have
let you-
Java 1 and 2 from before. We don't have any
Moment.
new slides.
I will just, out of curiosity, try to check what I have, because we still have a little time. No, it's not the one I want. Sorry, I have probably overwritten the screen. I will stop sharing for a moment because it's pointless. I will. I'm just checking now. Okay, I think that Dr. Walkowiak has been making changes to that page. I will contact him because, and I will, of course, I will publicize them. Sorry about it, but I was actually publicizing them, but the page has changed quite significantly quite recently from what I have seen previously, or maybe I was maybe it was my mistake. I don't know. Okay. Yes, all the slides will be available. Certainly before next week, I will make them visible to you. Okay.
Okay, thank you.
Okay, thanks. Any other questions? If not, then I will be ending this lecture. In a few minutes, we'll be meeting for the laboratory. So for now, thank you and goodbye.
Thank you. Goodbye.